So it's a great pleasure to introduce you to Slav Petrov. Slav is a distinguished scientist and a senior research director at Google. He's leading a globally distributed team that conducts natural language understanding and machine learning research. His work has been recognized with multiple Best Paper Awards and provides better language understanding to billions of users in a variety of Google products, spanning web search, assistant, ads, translate, and growth in Chrome. Thank you very much for your attendance, and the stage is yours, Slav. What we'll do is we're gonna be playing your video, right? And then you'll be here available for the Q&A. Thank you.
Exactly. Enjoy. I'm at Google. I'll be talking about work done across Google Research by many of my wonderful colleagues, and I'll be providing references at the bottom of the slides. So I encourage you to follow up on the papers, because this is really just a high-level overview of lots of different things that are going on, and the papers are where you'll be able to get lots more details. So I decided to give this talk, the title is Scale All We Need, because there's so much excitement around scaling of language models and the benefits that come with that. So if we look at nature and try to compare the scales of of our models to the number of neurons that different living beings have, we can see that actually ResNet and neural machine translation with attention are very much on the left side of the spectrum. Not even though we think these were big models at the time, they compare to the number of synapses that a fruit fly has. Then we had transformers and bird models with hundreds of millions of parameters that corresponds to a honeybee. And then we had GPT-2, T5 from Google, and models of that sort that are in the order of 1 to 10 billion parameters. And then GPT-3, and now also the M4 model from Google and on translation is in the hundreds of billions of parameters. And we even have trillion parameter models at this point. Oftentimes these models are then sparsely activated rather than densely activated, but we still have quite a bit of to go, several orders of magnitude before we can reach human level sizes. So one answer could be we just need to keep scaling, focus on the infrastructure, and figure out how to train these models in a stable way as they get bigger, deeper, and wider. And that's all we need. So that will be one answer to the question. And if we look at machine translation results, there's quite a bit of hope that this will give us actually significant gains. So let me unpack this slide, because there's a lot of information on it. So what you're seeing here is on the left axis you have the delta in blue score, so machine translation quality, and so this is the improvement over a baseline. And then on the right axis we have different languages, where languages are sorted by the amount of training data that exists for those languages. So on the left side, when we go horizontally, we'll have the high resource languages like English to French, English to Spanish, things like that. And then we'll have the core in the middle, and then we'll have the tail with languages where we might have only tens of thousands of examples of parallel data. And so when we train a massively multilingual model, so we pull all the data, we are clever about how we weight the data, because we don't want the the high resource languages to drown out the lower resource languages. And then we train this multilingual system. We observe gains across the board. So all of these lines are above 0. So even the high resource languages benefit from being trained in a multilingual way. But then we see, of course, the torso of the distribution benefits more. We see some very substantial gains for the small languages, 10 blue points and more. And then the different lines that you see, the different colors, they correspond to models of different sizes with different numbers of parameters. These are sparsely activated mixture of experts models. And we actually see a very nice and gradual improvement in quality as we scale up the models. On the bottom right, you have the average across the languages. And you can see the proportional scaling. Of course, it's not linear. It might be more logarithmic of some sort, but we see that as we go up to 600 billion parameters, the average blue gain is 13 points, which is huge. And so there's definitely value in scaling things up. And one way that we might be able to sort of benefit from this scale and extend beyond machine translation is to do multitask learning. The T5 model is something that has been gaining quite a bit of popularity. In a way, it follows sort of the evolution from transformer to BERT to T5. So BERT was an encoder-only model, and so it was very good for classification and for span labeling, but it was not good for generation necessarily. And so T5 is an encoder and decoder model, and so by prepending task descriptions to the inputs, we can train the model to perform different tasks while sharing the parameters across these tasks. And so one can start with the machine translation setup and add other tasks, or start with the monolingual model and add translation as a task. One can do question answering and other NLP tasks in the same model. And we do this during pre-training, and then either use the model as is for downstream applications, or we can do fine-tuning as we've been doing with BERT and similar models before. And so this works remarkably well, and I'll show some results later on. But it begs the question, what do we do when something goes wrong? Retraining these models is very expensive. It might take weeks on very expensive hardware that we might not have access to. And we can't do this for every single mistake. It's not very actionable. It's a very black box model. And so it seems worthwhile thinking about how can we sort of peel the onion, look a little bit inside the box, try to understand how it's working, and perhaps change the inner workings without introducing unnecessary constraints by adding some structure so that the predictions can be traced back and understood more by humans. And then therefore also controlled and adjusted when the behavior of the model is not as the way that we would desire it. And so I'll talk about memory, attribution, controllable generation, and how to model time, how to endow these models with the ability to use tools. And at the end, I'll spend a bit of time talking about trust and responsible AI in the context of these large models from my personal perspective. So let's dive in. Memory. Why do we need memory? We might not. I don't know. But it seems worth exploring whether endowing these models with a form of memory could improve performance, could make them more efficient potentially, and also whether it would help with the controllability and updatability of the model. So right now, the model is exposed to a bunch of text, up to 1 trillion words perhaps in training, and it learns from that text. And then once it has learned, the learning is in the form of adjusting the parameters of the model, then we use the model on downstream tasks. And the problem here is that we don't have a way to know what the model has learned. When the world around us changes, there's an election and there's a new president, we don't have a way of correcting or adding that fact. We can add one training example, but that's not going to overwrite everything that the model has seen before. And for certain types of things, it's questionable whether this is the most efficient way of representing the knowledge. So for example, the model might have crawled my website and might know my name, might even kind of vaguely know where I went to school, and have an association between Slav Petrov and UC Berkeley. But even if my birth date was mentioned or my how tall I am, it seems very inefficient and indirect to expect the model to remember these things. And if you think about how we as humans do it, we have perhaps a rough idea, like we memorize certain facts, but then for many other things, we know how to look them up. We know, okay, my friend's birthday is sometime in March, let me check my calendar, which day exactly it is. And so it seems natural to think about endowing language models with such abilities as well, and perhaps then trading off the parameters that go into the memory versus the parameters used for reasoning. It's okay. I think there's quite a bit of work happening in that space. We have some work at Google that I'll talk about, but I think there's a lot more that could be done here, and where perhaps the scale at which we can operate is not as prohibitive as purely trying to scale to 1 trillion parameters. So one line of work that sort of I'll be talking about started a few years ago, collaboration between folks in New York on my team and Pittsburgh. And so we were interested in learning representations for entities, and then using those for question answering tasks. So the idea is to try to sort of cram all the information that we know about an entity into a vector. That vector is not interpretable necessarily, but it hopefully still stores a lot of the information and the relationships that are relevant to a specific entity. And then when we use the model, we can look up entity spans in this memory and retrieve that vector and use it to adjust the predictions of the model. And one interesting thing here is that we can match the performance of an end-to-end sequence-to-sequence model with a fraction of the parameters. So we have only 95 million parameters that are being activated versus the fully activated T5 model, so it's 1%. And so this is more of a kind of proof of concept to some extent. And then we extended it to a paper that was published this year at NACO that is now adding facts. So in addition to the entities, we now have a fact memory that is structured, and where we can have structured relationships between keys and values. So a subject is the entity, and then there's a relation embedding, and that allows us to retrieve the value that has an embedding, and now we can add those into the inference of the model. And this fact memory is constructed from a knowledge graph. So the nice thing about this is now the fact memory is actually interpretable, because these triples come from a source that has labels that are human inspectable, and it is also on-the-fly updatable. So we can add new facts, we can update the facts when there's an election, when somebody divorces or somebody dies. We can add new facts and don't have to retrain the entire model because the entity representations and facts are outside of the core. And so on the right, you then see that it does better on the top graph just shows comparisons of T5 entities as experts and this fact-injected LLM work, and we see that it works better on the in-domain task. But then when we have a domain shift, when we change the topic, being able to, or change the time, being able to add facts to our fact memory allows us to get significant improvements in quality. Of course, these numbers are in the 40s, in some cases, maybe going up to 60, and there's a lot more that we need to do here to get these things to be reliable. Okay. And so continuing on in this direction of retrieval augmented models, instead of having continuous memories, we can also consider models where the memory is just natural language text. And so this line of work goes back a few years. Kenton Lee, Calvin Gu, and colleagues at Google, and then work from FAIR, building on that. I'm giving as a reference the latest work in that vein from FAIR, which contains the references to the systems that are being shown here. And the paper is actually on a slightly different topic, but I wanted to first talk about the results and then share some high-level thoughts. So let's look first at the red lines. And what we see here are the performance on OpenQA. So on Squad, we're given a document and we need to just find the answer to a question inside the document. In OpenQA, we don't have the document. And so we can either generate the answer directly from the parameters of the model, or in retrieval augmented approaches, we are allowed to do a lookup to a database of documents or sources, and then conditioned on then lookup, generate the answer. And so on the left, we have T5, and it gets 36%, which is quite substantial. And then we have two retrieval augmented models that do get performance in the low 40s. So the first thing is it's quite impressive that a model without an explicit memory is doing so well. At the same time, we can also clearly see that there are benefits for accuracy when we do retrieval. And I think there are also benefits for sort of trust and interpretability of the model when the model is allowed to do a lookup first. We can inspect the lookup, and if the system retrieved irrelevant information or outdated information, we know that the retrieval step was the culprit. If, on the other hand, correct information was retrieved, but the model hallucinated something, then again we know what needs to be fixed, or as a user perhaps giving the human access to both pieces of information, they can decide how to proceed. While the end-to-end model in this form doesn't provide any justification for its work. But that was sort of where things were before the EACO paper. And what Patrick Lewis and colleagues did was look a little bit closer at the data. And they found that there's actually a non-trivial amount of overlap between the training and the test set that can be captured with simple heuristics. And if the test set is cleaned of these redundancies, the performance changes quite a bit. So first of all, everything goes down. The blue lines are significantly lower. But the interesting thing is that the sequence-to-sequence model, it goes down much more. It goes down from 36 to 9. And the retrieval augmented models, they drop from 40s to 20s. So still a significant drop, but the gap now between the sequence-to-sequence model versus the retrieval augmented model is much, much bigger. And so we know that neural network models are very good at pattern matching, and that perhaps explains why the sequence-to-sequence model was so good at the task, because it was able to find answers in its training data, but it was not able to necessarily find answers in its general pre-training data. While the retrieval augmented models, they might not have as many they might know better what they don't know, and so when they do a retrieval, they can use that information to improve their performance. But the numbers overall are very low, so there's a lot of work that needs to be done to get this to human level performance. So when we talk about models exceeding human level performance, I think we need to keep in mind that the tasks are very narrow, and that oftentimes we have these implicit correlations that the models exploit and that make the task artificially easy. Perhaps easier for the machine than for the human, because the machine is optimizing the gradients during training, and therefore any correlation that is there will be exploited, while we as humans are actually trying to solve the real task and not necessarily taking these shortcuts. So now, switching gears a little bit to generation, like these retrieval augmented models, they condition on a piece of text and generate the output. And as long as the output is short, I think we have a reasonable handle of how to evaluate it, and also how to handle hallucinations or how to mitigate hallucinations. There's still more work needed there, but I think we're making good progress. Things become perhaps more interesting when we talk about long-form generation. Just get a glass of water. Okay, so in long-form generation, GPT-3 is amazing at generating very fluent text that oftentimes is also very coherent when looking locally, but when looking more globally, it might or might not be consistent with itself, and we have no way of controlling it. And so for summarization, we wanted to have a bit more ability to control and understand what the model is doing and build up the summary in a semi-structured way. And so the idea in this paper that was recently posted on arXiv is to do entity extraction and then use the entity chains as a way to guide the generation and the planning process. So during pre-training, we combine masking of sentences that need to be generated, as well as entity chain extraction and providing that as an additional information to the decoder, and can produce the desired outputs. And then we can do this during fine-tuning as well, where we stop the masking of sentences, but we still provide the entity chains. And then at test time, the model is expected to produce this on its own, but the entity chains allow us to inspect sort of the planning process and to perhaps interject if we're unhappy with something. And so I think that is a very nice way of benefiting from the great kind of fluency that is provided by language models, and at the same time put some kind of guardrails or put them on a specific track where we can condition on some information that we would like to see represented, rather than just via prompt where the model then can veer off in any direction that it wants. And so I'm excited to see more work in this direction, which I think will be needed if we want to use generation systems in practice, because right now it's beautiful and it's magic when they work, but when things break, it's very hard to know what to do and how to act on that. So I mentioned before time, and so now let's go back to sort of some of the problems that won't be solved with retrieval and with memory. Kind of injecting new facts was one way of updating a model, but in general, these pre-training models, they see a large corpus during training, and that corpus will span many years potentially. And so if we look at an athlete like LeBron James, he might have played for multiple different teams during those years, and the model will just have no choice but to sort of average over this information. Things that are further back in time, maybe they will be less represented in the data, and as a result, they might get forgotten. But recent events, who is the president of the US? Probably at the moment we have more training data for Trump being the president than for Joe Biden. And given that it's just the beginning of the Biden presidency and Obama was president for 8 years, perhaps even there's more training data about Obama being president than Joe Biden. And the model has no way of knowing that Biden is the current president, because the evidence, unless time is taken into account, the model can just average, and there's not enough evidence for that fact. And so in another paper that we recently posted on Archive, we were looking at how to potentially model time. And one sort of simple way of doing it is to just add timestamps to the training data. And so now every sentence is kind of labeled with information about the year that it was published in and that it was true. And the model can kind of condition on that when making its predictions. The results are promising, and we see great adaptation to new data as it becomes available, because the model is learning kind of some sort of bucketed notion of time. But I personally feel that kind of a lot more work is needed here. The sort of string representation of the year seems suboptimal in multiple ways. First of all, many things happen in the course of a year, so a year is not very fine-grained. And then there's no way for the model currently to extrapolate, because these are strings. And so if it has never seen anything from the year 2022, then it won't know how to handle that. And it doesn't know that 2022 will be followed by 2023. And so I think some continuous representation of time seems much more interesting to try to include, because these strings get mapped onto continuous values anyways. And so can we find a way to use sort of time as a continuous value, the way that it's represented actually in a computer, down to the millisecond, and use that as the label, or something along those lines, I think would be interesting to investigate. Another aspect that I think is important to consider is reasoning. So numerical reasoning is a simple example, but there can be other things that are of similar sort. So addition, arithmetic can be relevant for computing the answer to a question, or to executing a command of wake me up 30 minutes before my earliest meeting tomorrow. Unit conversions are another thing, like, oh, in New York today it's 100 Fahrenheit. What is that in Celsius? Or when you're cooking and it says use 12 ounces. I don't know what ounces are, how many grams are in 12 ounces. And so these types of things I think are very common, and they require just an execution of a simple arithmetic formula. And if we ask language models to do them, they sometimes actually manage to do the arithmetic and give an answer. So here's some examples from GPT-3. Kind of looking at the plot first, we see that kind of as the model size increases, there's a non-linearity, a kind of stepwise function where certain behaviors seem to be emerging, like two-digit arithmetic, two-digit addition or subtraction, and then three-digit comes later, and that's kind of cool. And at the same time, I don't think we really understand how it works, and I don't think the model really has learned the laws of math in a declarative way. It has just learned to mimic what it sees in its training data. And so a simple example is that the model gets the question to what is 1,000 plus 4,000 right, but when we flip the arguments to 4,000 plus 1,000, it gets it wrong. So it clearly has not learned that the arguments can be swapped. And it just seems, again, like the memory example, it seems very indirect to hope that these things will just happen in the model without us having a way to teach the model these abilities and for it to generalize. So some work that we did a few years ago, and unfortunately we at Google haven't pursued it much since, but I'm hoping we'll do more. And there's some academic work that has kind of looked into this task, is to just endow the models to use a calculator. And so we can extract argument spans and then call functions and then use the output of that function in our response. And so one could think of sort of generalizing this paradigm to not just arithmetic, but combining arithmetic, retrieval, and other API calls where the model needs to sort of decide, okay, what tool do I want to use, what are the arguments that I want to supply, get back the answer, and then generate its final response. And this would allow us to understand a little bit more what's going on under the hood. The challenge, of course, is that our pre-training data doesn't have many of these examples, so how to train these at scale is tricky. There might be multiple ways of arriving at the answer, and we don't have supervision, so reinforcement learning seems like a good way to do it, but there are probably others too. And so scaling this up and kind of doing it for a broad range of tasks is non-trivial, but I think it's a good direction to be thinking about. So, kind of now, I've mentioned sort of trust and responsible AI as one of the motivations for some of the things that I showed before, but for the final part of the talk, I actually would like to focus on trust as the main objective for the work. And so trust comes in a few different forms. Like it can come from managing expectations, the model being kind of robust and consistent, and not having any fairness problems. I think it can come from the model being able to explain itself and justify its work, and being interpretable. And finally, a model by itself will never be perfect. The data will never be perfect, the model will never be perfect by itself, but a product or a use case of a model will have a bunch of things that come before the model: pre-processing, control of the inputs, as well as post-processing and control of the outputs. And the machine learned component might be just one piece of a heavily engineered system. And so having policies that can be transparently explained and then enforced, I think, is also really critical. I like to use the example of the airline industry, where many people who go on a plane might not understand exactly the physics of how an airplane flies, and yet they feel safe on a plane because they know that the pilot was trained, that the airplane has been inspected and checked, that there's air traffic controllers who guide the different planes, and so on and so forth. And so I think sometimes when we think about ML, we're thinking too much about sort of the physics of flying, like understanding the inner mechanics of the models. And that is important, but I think it's just one ingredient of many. And if we want these models to be used in safe ways and to be trusted by society, I think we need to invest in the whole ecosystem and develop norms and policies that, that can be kind of tested and verified, and then we'll be hopefully able to make progress on deploying these systems to the benefit of everybody. So one kind of line of work that I wanted to chat about is a paper that we put up on Archive last year, which was focused on gendered correlations. So I think the term fairness is very kind of popular, and at the same time I think it's quite problematic, because sort of having arbiters of truth and arbiters of fairness, I think is very difficult. What is fair for one person might not be fair for another. I think we can oftentimes agree that something is less fair, and so reducing unfair biases, I think, is a good objective. But being able to sort of stamp something as, oh, this is a fair model, I think is not a good goal, because I don't think it's realistic. I don't think it's feasible, not from a technical point of view, and also not from a policy point of view, because we won't be able to fully agree. There's always room for maneuvering. And so I think in this line of work, we try to walk that line carefully, and we zoomed in on gender correlations for binary gender, because that's something that we can define well and then try to measure first before we mitigate. And so the kind of the main takeaways are from this work were that there are lots of unintended correlations in the model. Like, what it means to be intended or unintended is again something up for debate, like spurious versus non-spurious. Some spurious correlations might be innocuous and might be fine, others are problematic. And again, it will depend on the application as well as on the user as to what they perceive. But I think we need to understand these phenomena and figure out how to kind of mitigate them and adjust them. Causality might be one way of kind of addressing it. We only want causal relations to be discovered by the model, but that's a very tall bar, and maybe there are some kind of things that we can do in the meantime that are still sort of safe and good and pragmatic. So looking at the left bar chart, we have a few different models and performance on Tokenization task, and we see kind of there's some variance, but they're overall in the same ballpark. Kind of Bert versus Bert with more dropout, and Albert with more dropout. There's a small degradation from dropout, but not that big. When we look at the gendered correlations, however, and that's the second bar in the middle, we see that dropout drastically reduces the number of gendered correlations that the model has discovered. And so dropout is meant to prevent overfitting, and these gendered correlations are a form of overfitting, when a model, instead of relying on general features to make its predictions, has started memorizing names and other gendered terms to do a little bit better in terms of likelihood on the task, but as a result becomes less robust to domain shifts. And one nice thing here is that we are using demographic indicators at test time, but during training dropout is completely agnostic to it. And so we're not trying to fight bias by introducing a new bias. We're just trying to reduce the overall kind of overfitting aspects. And on the right hand, you can see another result from the paper where we try to do some counterfactuals and data perturbations to see whether we can make the model more robust by kind of messing with the data. And as I said before, this is kind of, when done right, it can be very useful. When done poorly, it can leave us thinking that we have fixed the problem without actually having fixed it. And so I'll just kind of talk about the first two lines. So on the right, the columns are the evaluation on names with the starting letters A to M. And then we have different sort of things that were done in training time. And so if we perturb the names, and we can see that when we randomize the gender, the last column, and the first row, when we have access to the same set of names during training as well as during testing, we can do quite well by reducing the gender correlation from 3.9 to 1.2 on this discometric. So that's kind of what I mean by, okay, this works when it's done, but when you have a match between the training and the test data, that can be also misleading because you're never going to have access to all the names in the world and that are occurring also in the pre-training data. And so the second row is, for me, the more interesting one, where during training, we only have access to names that don't overlap with the test set. They start with N to Z. And so we can see here that then we still see an improvement on the names from A to M. And one explanation is that the model has implicitly learned something like entity types and genders as a category of which these names are specific instances. And when we perturb the names between N and Z and flip their gender, the model learns to rely less on names in general, including names that it hasn't seen. And so that's a nice example that the model can generalize beyond the counterfactual that we are supplying, but the effect is not as strong as when you have the overlap. And so I think there's some hope, but a lot more work is needed in this space. A different kind of line of work that takes the idea of sort of retrieval augmented models that can explain themselves to the next step is QED, and that's going to be a TACO paper coming out soon. It's already on arXiv. And the idea here is that when you're in school and you're asked a question, it's not enough to just say the answer. We oftentimes want to see proof of the work and explanation of how the student arrived at that result. And so here we're trying to do the same for question answering, where we retrieve a sentence, but it's not enough to mark up the span. We actually want to generate a step of reasoning that explain why the model arrived at this. And so in a way it boils down to coreference resolution and entailment across noun phrases so that we can trace back what arguments are being needs to be found for which verb and which entity fills that so that the user can be sure that the model really understood the passage. Of course, these things become now tricky to annotate and tricky to evaluate, and it is not clear whether a regular sort of person, non-linguistically trained, would find these valuable, but they can be very helpful for ensuring that the model is making its predictions for the right reasons. And then looking under the hood and poking at the model is also very important, and we had a demo paper last year, and the tool is publicly available. It's called the language interpretability tool, and the idea is that you can load up a model load up a data set, and then try to explore model behavior, what happens when there are perturbations to the training, to the evaluation data, how can we visualize attention heads, can we cluster our data and see how the model behaves in different parts of the distribution, and so on and so forth. And so I think it's a very nice platform that is open source, and hopefully over time will be extended with more and more capabilities. Ultimately, of course, we would like to be able to sort of trace back, okay, this model made this prediction because of X, and X can be something in the input, or it can be something in the training data, right? Like, oh, there was this word in the input, and from these examples in the training data, we learned that triggers certain behaviors. And so I think this is the direction that we might be headed, but I don't think we have fully figured out how to do this in a consistent way. Finally, we talked about sort of policies briefly. I think both the controllable and the policies part here are important. Like, our training data will have good and bad things in it. I think scrubbing the data to make it clean is not the right way. I think we cannot pretend that certain differences don't exist, right? Like, we cannot pretend that there are no genders. There are genders in the world. And yet it's about what we do with that information. Like, we should not be discriminating based on it. And we should not be discriminating based on race. We should not be discriminating based on many factors, but we cannot pretend that those factors don't exist and that they're not observable. And so how can we break these implicit hierarchies that societies have created? I think it's something that we as humanity are facing, right? Like the BLM movement, which started in the US, but really is a world movement. I think we're having discussions how to do it as humans, and we need to hold the models to at least the same bar, to some extent, perhaps even to a higher bar than humans, and yet we don't really know how to do these, what the right policies are for humans. People are debating them, and so I think even kind of without knowing what the final policy will be, I think we need to do the research to figure out how can we provide the knobs and the controls so that then policy lawmakers, product leads can set the knobs to the right settings, and we as researchers will partner with them to explain what the knobs mean and how they affect behavior. But we need more controllability. Just training end-to-end models on data and hoping that, we'll just add clean data, I don't think is enough. I think we need to be able to deal with messy data and then post factum kind of tip the scales in the direction that we perceive as correct. So, hope you enjoyed the talk. Scale is important. Certainly we should be doing that, but hopefully I got you interested in some other things beyond scale, and provided some pointers. I did not have time to go into data set design, which I think is super important, and as well as evaluation metrics, because these models are so good at classification tasks. I think we need more sophisticated tasks, and generation is one way that kind of we're expanding the scope of these models, but with that, evaluation becomes a lot harder, and I think we really need to be very thoughtful in how we do this. Otherwise, we can fool ourselves that we're doing better than we are in reality. All right, thank you very much.
So I think something happened with Pedro. Thank you very much, Slav. for this nice presentation. A lot of new trends and ideas. We have here some questions in the Q&A. I don't know if the monitors want to help here. So I don't know if you can see here in Q&A. Do you have any rule for accepting? Oops, disappeared. Sorry. So the first question is, what is the numeric used for OpenQA? The metric used, sorry.
Cool. Hi, can you hear me?
Mm-hmm.
Yeah, cool. Thank you, Roman, for asking the question. Actually, can I share the paper here? So basically, for short answer, if there are multiple potential answers, we just look at the string match. But the details are described in the paper. Is there chat here? Or is there a way to answer it? Can I type? No. Okay. On the slide, there's a paper to Kenton Lee is the lead author of the paper. But yeah, I guess the tricky thing is that you can find the same answer in multiple places. And so we allow answers from a different passage as long as it matches. And that has become sort of the standard way for validating these things. Okay, so the people who ask questions, they can only type, they cannot ask clarifications or say whether they answered the question.
Yeah, it's in the QA tab. So the other one is like, do you have any rule for accepting, rejecting new information, or only the true information is passed to the network?
So I don't know which part of the talk this is referring to. Is this just about pre-training, or is it one about maybe the KG side of things? I think in general, we don't really know what true information is, right? And I think this is a really hard thing to even get right. Like there may be some things that are undisputed, like who is the current president of France is undisputed. But I just today was reading the news that Donald Trump still is kind of giving interviews or rallies where he says the elections were wrong and he's still the president. And so you can find contradictory information. And so I think it's very hard to know what's correct. Or another example is who invented the computer. Depending where you're coming from, you might get different answers. The Americans have an answer, the Germans have an answer. I'm Bulgarian, and there's a Bulgarian guy who also supposedly invented some programmable calculator. And so I think rather than trying to find the notion of ground truth, perhaps a different way to think about it is to sort of ingest information, but then be able to attribute it and say, I got this from this place. And now you can say, oh, no, but this source is not trustworthy, or I don't like kind of information from that source. I would like information from another source. And sort of the user has to choose what they consider kind of true. But most information, I think, is debatable.
Okay, so another question, how does tokenization work on numbers?
Sadly, nothing special is being done, and so it's just whatever word pieces are there. Yet another reason why I don't think that just feeding strings that represent numbers into a model and hoping that the model can do arithmetic is the right way to go about this. I think there are better ways to kind of feed the information in, represent it more correctly, and allow the model to actually reason with the numbers. And the experiments that I showed and things that people have done with GPT-3, these are just strings.
Okay, so for the film approach, when a new entity is added to the fact memory, is it embedding initialized randomly, or can the initialization be informed by related known entities?
Okay, actually, I can't see this question.
You cannot?
Which one is it? By whom?
So 1, 2, 3, it should be the fourth. From
what kind of data augmentation can we?
No, the previous one.
No.
Can you see the previous one?
No, the previous one for me is the true information.
Okay, so what I see is for the film approach, when a new entity is added. Can you see it?
Let me try to reopen it. No, I can't. But okay, so can you read? Is it close? Yeah, for the film approach, when
a new entity is added to the fact memory, is it embedding initialized randomly, or can the initialization be informed by related known entities?
So I guess there are two parts here. You can add information about existing entities and relations, in which case you already know the embeddings of the entities and the relations. And then the way that the film memory is constructed is actually compositional. And so then you can kind of compute the representation of that. If you have a new entity or a new relation, that wouldn't work because you wouldn't have a representation for the entities or for the relations. And in that case, I actually don't know what folks did, whether this is even supported or whether we only allow to add information for known entities and known relations. I would defer to the paper and encourage you in general for all of these papers. You'll notice I'm not an author on any of them, so I know the work reasonably well, but I might get some of the details wrong, and I'm very sure that the authors would be very happy to answer questions if something kind of is a little bit unclear in the paper.
Okay, so the next question is at 543. So what kind of data augmentation can we do in order to increase fairness? I'm thinking of computer vision, where basically we force the model to learn rotation invariance by randomly rotating pictures. Can we randomly replace E by she or similar techniques?
Yeah, so the parallel to computer vision is interesting, and it's sort of in some cases, I think it's easier to think about these things in the vision space, but then to also visualize the shortcomings, right? Like, so if you wanted to create a balanced data set of faces, because you want to do some type of face recognition, you could balance it based on gender, right? That would be the first thing to do. But then what about skin tone? What about hair color? What about hairstyle for males versus for females, right? Like there are women with short hair, there are men with long hair. What about nose shapes? What about eye color? And it becomes, I think, quickly obvious that you can control only for some high-level attributes, and that you will have kind of imperfect data along other dimensions. And a risk that comes from sort of synthetic data generation or augmentation is that you try to make the data more uniform along one dimension, but as a result, you might introduce even more severe biases in another dimension, right? Like if you start adding female images to balance it, because let's say you had more male images at the beginning, and if you don't carefully control to sample from the right distribution or for control for the right attributes, you might add more women from a specific subpopulation and thereby introduce a very strong correlation with some other feature that the model will then pick up on. And so I think similar things can happen on the language side, right? Like you can talk about, you can replace the pronouns, you can make sure that the documents that you introduce in the data represent the world in a more fair way, but it's really hard. Like we consider Wikipedia as a sort of trustworthy and somewhat objective information source, but the reality is that when it comes to people, 80% of people covered in Wikipedia are male, and only 20% are female. And the articles tend to be also shorter for the females. And so now kind of, if you go deeper, you can actually see that even when you scrub the names and the gender-carrying pronouns, you can still build classifiers that can detect whether this article was originally about the woman or about the man because of the adjectives and the other constructions that are being used, the types of attributes that are being described about males versus females. And so gender is conveyed in many, many subtle ways in the text. And so scrubbing the high level things like pronouns, I think, can create also a sense of false kind of progress. That we need to be careful with how we manage it. I think it's good to look at it, but ideally we try to find something that goes deeper and really tries to we try to develop techniques that can deal with imbalanced and imperfect data sets.
Okay, thank you. The next one is, what are some open questions in constraint generation or control knob settings that you discussed later in the slides? That's 5:53 p.m.
That I discussed later in the slides. I mean, sorry? Yeah, Mariana?
Just remembering that was about constraint generation and control settings.
I mean, so you can kind of, for constraint generation, so like you can put constraints on multiple sides, right? Like you can put constraints on the input side of like, okay, here's a structured information source. I want only things that are represented in the source to be covered on the output side. You can then, on the output side, control for style. It can be formal or informal. You can try to control for dialect, right? Like machine translation quality is getting better and better, but we are kind of lumping in all the variants of English, all the variants of Spanish in one pot, all the variants of Portuguese. And like we have lots of Portuguese speakers here, and kind of Brazilian Portuguese versus Iberian Portuguese is mutually understandable, but it's not the same language. And so can we try to control for that? We can try to control for verbosity, like length. Like sometimes you want really a crisp answer. Like if you're talking to an assistant device or some type of dialogue system, in some settings you just want crisp, short answers. In some other settings, you might want a bit more explanations. It might also depend on the user. Some users prefer just the minimum information, while others want to get more context. And so these are some of the knobs that one might be thinking about.
Okay, thank you. And at least, okay, so we have two more at least. At 5:56, could you speak more to how providing controllable policies for model is a better approach than trying to train on clean or fair data? And thinking that if only a select number of people are able to control the policies, there's still the issue that a small group of people are defining what's fair to a large group of people, so they might not be able to account for the messiness or the diversity of the real world. Thanks.
Yeah, so I mean, I agree with the second part of the question, and if I knew how to create fair data, I would love to do that. But as I was describing sort of in the image case, I think it's just really, really hard to create a perfectly fair and balanced data set. And like I was just reading a book on by a social scientist, like on diversity, and I think sort of the fairness, unfairness parts come not from the attributes that are present, but I think they're oftentimes sort of social constructs and sort of an implicit or explicit hierarchy that societies creates. And that's the problem, right? Like if you see somebody on the street and they have brown hair or kind of light brown hair or dark brown hair or black hair or blonde, right? Like there are societies where there are implications with this. But in general, sort of a kid that sees people with different colored hair and different colored skin doesn't have any value judgment associated with those properties. Eye color, right? Like, yes, blue is sort of rare and considered maybe prestigious, but nobody will sort of comment on somebody's eye color in a derogatory way. But people will use body shape and other things in negative ways. And so I think we can't erase those things. The world comes in different forms and shapes, and people come in different forms and shapes, but like we should not be using it in discriminatory ways. And so I wish we could kind of make everything super balanced so that if everything is maximum entropy and uniform, then there's no single characteristic that you can pick on and work on. It's somewhat arbitrary, but because things are not uniform, certain features might get used in bad ways. And so I agree that having a small number of people set policies is suboptimal. We tend to think that the government is sort of fair, and we know that there are biases there as well. Like the Black Lives Movement has, I think, opened people's eyes quite a bit to that. And so how do we kind of, create more representation and fair processes, I think, is something that we as computer scientists and we as just people living in societies need to advocate for progress. But kind of how to fix it, it's going to take time.
Because of the time and Slav, because of the time, maybe we can just answer one more question. The remaining questions we're going to put in the channel, in the Slack.
Okay, people are asking more. Okay, yeah, let's do whichever.
Maybe the one that came first, 6 p.m. We know that English is one stable language for current NLP research than others. What do you think that all approaches that we explained before can be used to other languages?
I mean, I think the approaches in general should work for other languages. In practice, I think we're investing way too much time on English and less time on other languages, kind of considering how many other languages there are and how much they're spoken by people. Like, I think we're spending 80% of our effort on English and 20% on other languages, and perhaps it should be the other way around. But that's another sort of bias that exists in the world, because the rich gets richer, right? It's the language that most people communicate in nowadays, at least in scientific communities, and so that's why we see more work in English. I think approaches that sort of discover patterns in data automatically are beneficial. But when you think about tokenization, for example, word pieces work so well for English because English has specific properties, that it doesn't have much morphology, and as a result, you don't need to model it as explicitly, and you can get really good performance. And it works reasonably, kind of standard word piece tokenization works reasonably well for non-English, but you can do much better. And there are a number of papers looking at byte representations and kind of general tokenization-free approaches. There's some nice work out of Google as well on this. Byte 5 and K9 were published recently. And I think these types of properties of languages, we need to embrace them and think more about kind of how to make the models as general purpose as possible so that they can capture all the nuances of the different languages, because that's the beauty of language, that it varies so much. But I can only encourage people to work more on non-English.
Great. Slav, in the name of the organization, I'd like to thank you for the nice and very interesting talk. And we are going to close the session, and I invite other students to continue with the school program tomorrow at 9 a.m.
Thanks, everybody.